Hi, everyone. I want to go through a brief introduction to some common terminology and notation that we use in probability before moving on and applying some theory from probability to analyze statistical questions. And so recall that statistical inference is the process of using data from a sample to describe characteristics of the population. And since our conclusions are going to be based on sampling, on randomness, we're going to need to account for some uncertainty in the predictions that we make using statistical inference. But statistics relies on theory from probability, and we're going to use that to help quantify the uncertainty in our models and estimates as we move through the material this semester. And so if the terminology, probability, and statistics is confusing, these are different fields. And so if we know the makeup of a population, we can use probabilities to predict the likelihood of certain outcomes. So for example, if we know a six-sided die is fair, then we can calculate the probability of getting certain outcomes from that die, such as if we roll the die 10 times, we could calculate how likely we are to get exactly 4 rolls that land on 1. We use statistics to go in the reverse direction, namely, how can we make predictions about a population from just one random sample? So if we want to determine whether or not a die is fair, that's a question about a population, we can collect a sample of data, like rolling a die 100 times, and observing that we got 40 rolls that land on 1, and then we can consider whether or not it seems likely that that result came from a fair die or whether that die is biased. So some common terminology in probability and notation are things like sample space, outcome, and an event. And probability is an application of set theory. So the sample space we denote with the Greek letter omega, and that is the set of all possible outcomes from an experiment. An outcome we denote with a lowercase Greek letter omega, and that would be any one individual result from an experiment. And an event that we denote typically with capital letters, in this case, A is like a generic event, is a collection of one or more outcomes from an experiment. And so probability, this really sprung out of studying dice games. So let's consider a dice game to get us going. And if we are rolling a typical six-sided die that has numbers 1, 2, 3, 4, 5, and 6 on each face of the die, then the sample space, if our experiment is rolling the die and looking at the number that appears on the face up of the die, the possible outcomes in the set capital omega would be the numbers 1, 2, 3, 4, 5, or 6. So this is like a discrete set of outcomes. Each outcome would be denoted with a lowercase omega. So for example, if we were to roll a 4, that is one outcome, and we could denote that by saying lowercase omega is equal to 4. And an event such as that the result of the roll is a multiple of 3, there are more than one outcomes that satisfy that. In fact, there are 2. If you rolled a 3, or if the result of the roll was a 6, those are the 2 outcomes that we could get that are a multiple of 3. So that means we've got 2 outcomes in the event A. And the die example, this is an example where if we assume the die is a fair die, then we can assume that each of the outcomes in the sample space is equally likely to occur. So in that case, we could calculate the probability of any event A by counting up the number of outcomes in event A and then dividing that by the total number of outcomes in the sample space, capital omega. So we use the notation P of A to denote the probability that event A occurs. And these probabilities, these are proportions that have to be between 0 and 1. So we can't get a negative probability, and we can't get a probability which is larger than 1. So we can denote the probability as a function that maps outcomes and events in the sample space omega to a real number that is between 0 and 1. So it's going to take each event, each subset of the sample space, and map it to a proportion between 0 and 1. And so sometimes we represent these probabilities as proportions, as decimals between 0 and 1. Sometimes we represent them as fractions, and sometimes we represent them as percentages, depending on the context. So let's take a look at an example. So question 1 is asking if a person rolls a fair 6-sided die, so each outcome in the sample space is equally likely to occur. What is the probability that the result of the roll is a number that is a multiple of 3 or is divisible by 3? In that case, we could take a look at the full sample space omega, and we can compare that to the size of the event A. So event A has size 2. Omega, the full sample space, has 6 outcomes. So therefore, our probability would be 2 divided by 6, or 1/3, or approximately 33%. So that's a little introduction to some of the terminology and notation that we use in probability theory. This document that I worked through, you can find the link to this document in the description of this video, and there'll be a continuation of this in a separate video where we actually use these ideas from probability theory to analyze a data set of melanoma patients.